Welcome to Brain Vision.
So this problem has us looking at the magnetic field produced by a segment of a ring. So this ring has inner radius r1, outer radius r2, and then it's an angle theta of a full circle. And so at point C here, which is at what the center of the ring would be if this was a complete ring, we want to find the magnetic field. So this looks like a Biot-Savart problem to me. Because we don't really have good circular symmetry like we sometimes get, which can work well for Ampere's law. But we do have all of these kind of very clean wire lines that we could integrate across to get our total magnetic field. So we'll label these. We'll say this is wire 1, wire 2, wire 3, and wire 4. And so as usual, we want to find our total magnetic field. And that'll just be B1 plus B2 plus B3 plus B4. So it's almost always easier to break these things into different regions than look at each region separately. And especially here, because if we're doing the Biot-Savart law, that tells us that the magnetic field from one of these little regions is mu naught I over 4 pi, and then the integral of dl cross r over r squared, where dl is a little infinitesimal length of one of these wires, and then r is the vector from the point we're looking at out to that part of the wire. And so the reason this is extra helpful to look at is dl cross r. If we look at regions 2 and 4, well, here L and R are always parallel to each other. So if we draw out an r vector from here out to here, well, that's exactly parallel with wire 2 and would be exactly parallel with wire 4 as well. And so the cross product gives us a sine of theta, where theta is the angle between those two. So that's always going to be parallel or anti-parallel, depending on which way we're going. And so that has to be 0. So that means that regions 2 and regions 4 can't give us a magnetic field at point C. So we only have to worry about 1 and 3. So that simplifies things a little bit. So now we'll just apply the Biot-Savart law to those regions. So we're going to have mu naught I over 4 pi for both of those, and then just times this integral as applied to region 3 and region 1. So we'll start with region 3. So we're integrating from 0 in terms of both angle and r radius out to a full radius r1 and an angle of theta. And the big thing to recognize here is that dl cross r, well, dl is always going to be at a right angle to r, given our wire here. And so really this dl cross r is just a path integral. So it's just kind of what's this length. There's a line integral rather. So it's just how long is this section. So we're just integrating ds, we usually call it, and then over r squared. And so then we have the same integral, but for the farther away region. So ds over r squared. The one thing we want to keep in mind is for region 1 here, we want to check our sign. So region 3, the current's flowing this way. And so if we do the cross product of dl cross r, first we point our fingers along dl, and then we curl them in the direction of r. And the only way we can do that is with our thumb pointing into the board. So that tells us that this one is going to be positive, since into the board's positive. Whereas when we do the same thing for region 1, we find that it's negative. So we get a negative sign in here. And so we have mu naught I over 4 pi. And this ds integral is easy, so that's just going to be this path length. And so that's just theta times r. And this r here we don't have to worry about because that's always a constant distance from here. So in the first case, that's always distance r1. In the second case, it's always distance r2. So we can even write those in right away. So normally that would be something we have to worry about in the integral, but because of the symmetry here, they end up being constants. So we're just integrating ds, and that'll be theta times r. and that r will be r1, and then over r1 squared, and then we have minus theta, and then r2 over r2 squared. So the exact same thing for the other one, we just had that minus sign. So this looks like an okay way to write it to me. If we wanted to simplify it a little bit more, we could combine these fractions. So multiply this first one by r2 squared divided by r2 squared, and then multiply this one by r1 squared over r1 squared. And if we did that, we should be able to get this into something like this. So mu naught I theta over 4 pi r squared. We could pull out the theta now even. And then we'll have, oh, sorry, no r squared there. And then that would be times r2 minus r1 over r1 times r2. And this whole thing is in the k hat direction, so into the board, positive into the board, negative out of the board. So this is maybe a slightly cleaner way of writing it. So no r squared there, remember, r2 minus r1 over r1 minus r2. But I think this is a fine way to write it as well. So just kind of your preference.